Okay, with luck, we're now recording. Good. Welcome back. So today we're looking at regression. And so this is one of the things that you'll hear from me throughout a lot of this course is I will be relating lots of the network algorithms back to regression. And people have heard me speak about this in public forums. I will frequently say that neural networks or distributed computation or artificial intelligence or whatever is just it's a nonlinear form of regression. It's a nonlinear statistical method among many nonlinear statistical methods. And it has the distinction of being a nonlinear statistical method that was developed from inspirations in biology, and therefore is not understood all that well. And as opposed to other statistical methods, which are understood very well, so that I will try to link ideas that we have in computational learning. Sure, I need everybody muted. Okay, there we go. That'll fix it. So I'm going to try to link the many of the ideas in machine learning to these techniques as best we can from statistics, and try to teach how to do that. This chapter is a little dense, and I apologize for some of the ways that Haken wrote it. He is following a very traditional statistical approach to this, and I will go through this, but I'm going to do it in a slightly different way. And again, I will talk about some of the questions that have come up about the homework, but also as usual after the end of class, I will keep the Zoom open if people have specific questions about the homework, and I will review that and get hopefully grading back to you in the next couple days. So the first thing to notice, and we saw this before, is that the sort of McCulloch-Pitts style neuron looks exactly like, the equation for that looks exactly like standard regression equations. And we see this happening all over the place. Let's see if I can give a sense here. If you look at this type of equation here, excuse me, let me change that type of equation there, that is a very standard sort of neural network equation. Oh, by the way, I just uploaded a blank version of these lecture notes to the to Canvas if people want to, if you want to take your own notes on it, but I'll also upload the marked up version later. So again, this is a very standard. The difference here is this sort of error term there, but certainly W, there's no, we're using W to indicate weights, and this would be a very standard regression model. The difference is when you do a regression model, you assume that you have some observations, which might be the output of the network, and you have some inputs to the network, these X terms. And then the epsilon term there is sort of the error, and we say that that's the complete characterization of this. Not all error is additive. And it's going to be very important to recognize some of the assumptions that come along. So this is an additive type of error. Many types of noise in the environment are additive, but of course there's many types that aren't, and we can look at that perhaps a little bit later in the course. So when we look at these, there are, because the McCulloch-Pitts neuron, or the standard sort of linear neuron, looks exactly like regression equations, you can imagine there are going to be many aspects of this which will share, the results will be shared. And of course, this chapter spends a long time looking at many of those issues. The terminology in statistics, of course, is somewhat different. X in this case would be considered the regressor, which is the thing being regressed on, in some sense, and then you'll have an outcome variable, which they're listing as D here, or we often use Y. And then there are these sort of parameter vectors, which might be considered the coefficients, or in statistics are sometimes called the weightings. And then we get into these idea of what's Bayes' law, Bayes' rule, and that's the first way that this is approached. And Bayes' rule is very important. There are Bayesian networks, but Bayes' rule is more important just because it makes explicit this idea of what are your assumptions prior to how do you incorporate prior knowledge into an estimate. And well, let me come to that in a second. The first thing I wanted to do, however, is before going there, just to briefly review some of the very simple statistical terminology that you guys have seen. I hope most people are familiar with this. If you're not, I can point you to things, and of course, there's tons of stuff online that goes through this. But generally, you want to distinguish, and I'll make comments as we go, between sort of discrete and continuous probability densities. These things actually have very different properties to them. A discrete probability density is probability of xi, where xi are a discrete set of events. You are, you know, you pick a ball out of a bag, and it's either blue or red, right? It's not something in between. It's one or the other. So an event might be I observe a blue ball. An event might be I observe a red ball. In continuous probability densities, you have this idea of a function p of x, where x is a continuous variable. And one of the things that confuses people quite a lot is if I have a continuous, I've got x, and so this is where I can make my handwriting a little bit better. And if this is p of x, and I say, okay, what's the probability that that value of x occurs, right? And the probability that the value of x occurs is always 0, right? In other words, if I have, if x takes values between 0 and 1, and I say, you know, what is the probability that I observe exactly the value pi over 3, right? That the probability of observing that 0, it'll never be exactly pi over 3. It could be a little bit off, right? That's never an observation that's actually going to happen. So the probability of that when you're dealing with a continuous distribution, the probability that x equals x, where x is continuous, is equal to 0 always. Okay, so how do we solve that, right? So, and again, most of you have seen this, but I want to be very explicit about some of the statistic assumptions that make this happen. The way that you solve this is an event is never that precise. All events are measurements or events you can see in the world. So you can't measure the value, you know, x equals pi over 3. That's not something you can do, right? But what you could do is you can say, what's the probability? Well, you could measure an event that says x is between some value. So it could be between 0.5 and 0.6, right? It could live in that interval. Or it could live in some very tiny interval. You could have a much more precise value. So maybe x lies in some interval which looks like, you know, I don't know, e to the negative 10th and e to the negative 10th plus e to the negative 11th, right? I mean, that's a perfectly valid interval, right? It's a very small interval, but it's nevertheless an interval, and it's a finite interval. And so when you talk about probabilities, you're always talking an event in continuous probability domain is always a range. It's always there's always uncertainty. There's always a size of the dot on the thermometer, right? So because of that, the probability of events in continuous probability densities is not a dot. It's a region, right? So if I have a probability here, the probability that x lives between this point and that point is actually the area under this curve. So then we talk about the probability that, you know, x lies in some region a to b is the integral from a to b of the probability of x dx, right? And so these are just the definitions, and that's how we deal with continuous probability densities. But it's very important to realize that. And this comes in, you'll see this in a number of places. So there's one point where Haken points out that estimates are in some sense regularized by the addition of noise, right? Noise makes you uncertain about your measurement. It's the uncertainty in the measurement that allows them to have probability. In other words, it's because your measurement exists in a range that it has a non-zero probability at all. And there's lots of ways in which you can be uncertain, right? One way to be uncertain is that you just, you know, the markings on your thermometer it's discretized, right? You have a discrete measurement. I'm encoding a value in an 8-bit number. That's a discrete measurement, right? So if I have an 8-bit number, I can only distinguish intervals of size 1/256. And so I can look at, and those things have finite probabilities. But I could also ask what is the probability that x is approximately in this range? Because, for instance, if you look at this is a square function, right? But I could also ask, what's the probability of x living in a little window like that, a little Gaussian window like that, right? And I can take, here's my probability function, p of x, and I can just look at the area defined by the product of those two. And so which is exactly the same thing I did here, just here I did it for a boxcar function, here I'm doing it for a Gaussian. So that, again, but it's very important to recognize what that means. Now, when we start looking at the, at some of the things that make probabilities what they are, this is in the discrete domain, the sum of all the observable events has to equal to 1. So it's going to be the same thing in the continuous domain. The reason it occurs in the continuous domain is because what you'll do is you will take the you'll take your continuous distribution here, and you're going to take some region like that, and you're going to add up the next little region, and you're going to add up the next little region. And when you add all of those up, eventually you're going to get the integral over the whole thing, right? So no matter how you chop up x, no matter how precise your thermometer is, or how precise your measurements, or whether you're 8-bit, 16-bit, 64-bit, whatever it is, no matter how this is chopped up, the sum over all those events has to equal 1, which is the same thing as saying the integral of the whole thing is going to have to equal 1 in the continuous domain. Does kind of make sense? This is, most people have seen this. I just realized that when you start talking about probability, there's a lot of confusion over what these things actually mean. What do probabilities mean, right? And so remember, an event is always this is the formulation from Kolmogorov. There are two concepts of probability theory. There's sort of the Kolmogorov probability, and then there's sort of quantum probability. So those of you who studied any quantum mechanics, this is a very different concept there. We are going to be looking at the Kolmogorov concepts of probability. But this is all based on set theory. Just to give again a little bit more background for this, and because when we're all in high school and people are sort of wondering, you get these probability paradoxes, and people are always wondering about this. Where does this all come from? What does it mean for there to be sort of truth in the world, or when you can only talk about probabilities as ranges? The way to think about this is in real probability theory, there's a probability space, generally referred to as omega. And there is truth. There is a state of the universe, right? It may not be measurable, but the idea is that, unlike in quantum mechanics, the state of the universe is considered to be measurable. There is an actual value. The problem is, all you can do is observe events, and events are sets. And the series of observable events are going to be things that include the actual truth of the universe. But an event would include other possible truths as well, right? So any measurement, anything you can see with your eyes, anything you can measure in the laboratory, always has a group of possible truths that could be part of it. And you can imagine that the difference between an event that looks like this and an event that looks like this, if truth is in the middle, both of those things are true, but the smaller event constrains truth a little bit more, and therefore in some sense conveys more information. And that's the equivalent of making a more accurate measurement, right? If the temperature outside happens to be 80 degrees, and I measure it with a thermometer that measures by single degrees, or it measures by 1/10 of a degree, I may get 80.0 on one thermometer, and I may get 80 on the other. Truth in the world is the same, but I have a more accurate estimate and a better sense and more precision about where I think I am. Right? So again, this is at some level there's always it's always a set. There's always a discretization, even when we're talking about continuous probability densities. Okay. This, hopefully over time, this becomes more familiar to people. Probability theory is not what you think it is. And this also becomes true when you talk about how does probability change under observation, and we'll talk a little bit more about that. I don't know how much stochastic systems I'll do, but in stochastic systems, people spend a lot of time thinking about these. Now there are a few things that happen in continuous probability domains that are worth knowing. Well, or just terminology that's worth knowing. The expectation operator. Let me get The expectation operator, and there's a continuous and a discrete version of it, right? The expectation operator is basically it cares about probabilities are always within, they always live within 0 to 1. They're always positive numbers, right? And they always live in that range. But, and they have this meaning. Whereas the value of X could be anything, right? X could be a color, X could be a sound, X could be somebody's name, X could be anything. So the expectation operator, and in this case, the expectation operator requires X to be something that lives on on some kind of a ring or an algebra where you can add. But realize that the values of X could be in any units. It doesn't matter if that's in Fahrenheit, centigrade, furlongs, that could be any units it want, but you can always calculate an expectation operator. Right? And again, just recognizing that these things are sort of living in different spaces. When we look at in continuous domain, of course, this same equation becomes an integral. Right, and it's an interesting integral, right? Remember, I told you that if I look at X and P of X, and so now I have P of X as some kind of probability, the integral of P of X dx equals 1. What does it mean to look at the integral of X times P of X dx, right? So I take, I'm basically multiplying these two functions by each other, and I'm the product of those two functions. I'm taking the integral of that, and that in some sense will say, well, suppose that the probability, suppose that the probability density looked like this. These are the values of X going up like that. If I take the product of these, I'm basically going to sort of emphasize values of X near the middle of this probability distribution. And that emphasis is going to say, okay, that's the expected value of X, where I'm going to get a number out of this. This is a scalar value that comes out of that integral. And that scalar value is the expected value. We think of it as the average. But again, you want to think a little bit deeply about what does it mean to be calculating averages in these contexts. Now, if we look at, there's a terminology issue that happens here. And again, I'm not going to use this very much, but you may see it in other contexts. Those of you who are familiar with the concept of the Lebesgue integral, these are typically written as Lebesgue integrals. The important thing about this is, what does this dp mean? The dp, if you differentiate it, dp of x, p dot of x dx, looks like p of x dx. So these things are just equal to each other, right? All I'm doing is, if you could just substitute one for the other. Integral of x dp is the same thing as saying of integral of x p of x dx. It's essentially saying that, what does the dx term in an integral mean? The dx term says, as we in a Riemannian integral, it says, how do you move along the x dimension? How do you chop up this x dimension, right? And what I could do is, if I have a probability density that's doing this, suppose that's P of X, right? I could say, I'm going to make P of X, I'm going to chop it up in a way that's proportional to P of X. So I'll chop these guys up a little bit. I'm going to change the way I write this a little bit. So suppose that P of X does something like this. And I could chop up this interval and make these guys, in some sense, very, very small, and these guys very big, and these guys small again. And I could just chop that interval up in different ways. And probably a better way to think about it is actually the opposite of that, which is that these, because P doesn't change very much in it, it's like having this being a larger interval. And because here P of X is changing a lot, I'm going to be very fine-grained about that. But the point is, what you're doing is you're squishing, you're spreading out the x-axis. Let me draw that again. So if I have, suppose that this is X, that's P of X, and this goes up and down like that. Okay, that's a probability of these things. And now suppose that I say, okay, I'm going to remap, I'm going to set my numbers on the x-axis in the following way. I'm going to make these very broadly spaced, these very narrowly spaced, and these broadly spaced again, right? Now I could say, what would happen if I now squished out, I spread the x-axis, right, into P inverse X. If I were to spread it out in some way such that all of these little intervals became equal, right? What would happen? So now all my x's look like this. And that means I'm sort of spreading, I have to squish this, right? So now my P of X is going to be really squished out like that. In fact, it's going to be flat, right? If you set it just right, it makes it flat. So what it does is it says, and if you look at what happens here, the integral of P of X dx, sorry, just again from the terminology, is the same thing as looking at dp of x, or we could write that as the integral of 1 dp of x, right? So spreading out the axis is the same as instead of integrating p of x, I'm just integrating 1. Right? And so so really what happens here is this is flat. If you do it properly, if I spread out this, if I changing the axis, changing the stretchiness of the axis in different places is the same thing as changing the shape of the probability density. Right? Again, this is, you don't have to, I kind of want to let this wash over you guys, but when you're thinking about continuous probability densities, realize that a probability density is considered a measure. It measures, it says where is there probability in the world. And very importantly, what we're going to see when we start looking at networks and trying to train networks, you're going to run into the situation of saying, where do we want to focus our learning, right? You don't, in a lot of cases, there are situations where you want to focus on rare events, but usually you want to spend most of your time learning about the things you're most likely to see. And so often there will be situations in which you will literally spread out, you'll warp the input distributions in ways that will spread out the data that you care about the most. And that's literally what's happening here. You get the same values, the same answer, but spreading these things out may be very helpful in terms of actually doing computations. But in the first lecture, I talked about this issue of the input warping, where you might have a first layer in a network that figures out what are the important variables, what are the features. And feature detection is exactly this. Feature detection is a mapping of the input space that attempts to emphasize parts of the input space that are important in some way. In this case, what the probability density does is it emphasizes the parts of the input space that are important in the sense that they're more likely to occur. That doesn't mean they're the most important things you care about. Sometimes highly likely things are really boring and don't lead to difficult learning problems. But sometimes highly likely things are very important in terms of minimizing your overall error. Okay, that's probably more probability theory than you guys needed, but just to encourage you all. There's a lot of fun. There's probability theory is it's closely related to an area of integration theory called measure theory, and there's a tremendous amount of work that's been done on this. On to Bayes' rule. So the definition of conditional probability. Bayes' rule is neither it is not a theory. It is just a mathematical truth. How it is applied is a matter of theory, but Bayes' rule emerges directly from the definition of conditional probability. So this is the definition of conditional probability. So the probability of A given B is the joint probability of A and B divided by the probability of B, right? And the reason why is that the definition of conditional probability? So what happens is, let's suppose we have two values, A and B, and we've got, some kind of probabilities in here. Let's actually, I'm going to write this the other way around just because it'll make it easier. A, B. And let's suppose that I have a probability density in here that's kind of roughly shaped like this. So a lot of the probability mass lives in some region like that, right? And I said, okay, and this is the joint density of A and B. So that if the probability of observing this A and that B is given by the value there, right? So these are, so that's the joint density. But what I want to know is, after I've observed a particular value of B, what's the probability of A, right? So that's going to be just a function of A. Probability of A given B can be thought of as a function of A parameterized by a particular value of B. So I've observed a value of B, and I want to know what's the probability density of A. Well, it looks a little bit like this, like sort of a vertical bar there, right? But the point is, what is that that vertical bar, there's nothing about PAB that says that that vertical bar has to satisfy the integral equals 1. So how do you get the integral to equal 1? You literally divide by b, and that makes the integral work out. So literally that's all you're doing. You're taking a slice of this, and you have to normalize by probability of b. So it's probability of a comma b divided by probability of b. You just have to normalize by that denominator, otherwise you don't get the integral of 1. But if you do that, then you get this probability of a given b, which looks like a probability density over a. And again, I'm doing this in the continuous domain. If you really wanted to do this, you would see it's not really b, b is in an interval here. What's the probability of a given that b lives in this interval? What's the probability of each little interval of a given that b is in that interval? But it turns out that it all works out if you just write it in the continuous domain. But again, always remembering what is the actual probability of b? It's 0, right? But if p of b is a density, then you can divide by the value of the density at that point, where what I mean by density is this continuous function, p of x or p of b. Okay, so now if we look at that, we can write the probability of a given b, and you can also write the probability of b given a, right? It's symmetric, because again, here I can estimate a from b, or I can estimate b from a, right? I could say, what's for this value of a, what's the density of b? Those are perfectly reasonable. And you could just rearrange these and show that the joint probability of a and b is the conditional density of a given b times the probability of b. Conditional density, the joint of a and b, it can also be written p of b given a times probability of a. These two things are equal to each other, so I can set that equal to that. And then I come up with Bayes' rule, which basically says, what do I have to do to convert from probability of b given a to the probability of a given b? What's the difference between these things? And it's determined by this ratio, PA over PB. Yeah. And so that's basically Bayes' rule, right? P of a given b is equal to P of b given a times probability of a, sorry for the handwriting, as always, divided by the probability of b. Okay. And it's just, so it's a very simple thing, right? There's nothing magic about this. And the fun all comes down to when you start trying to interpret what these things mean. So now let's start looking at what this might mean in our context if we were to look at this. So now consider that we have a data set D, and I'm going to write this a little bit different from the way that Haken does it, but it's essentially the same formulation. So let's say D is an observed data set which consists of inputs and outputs to a network, right, or just to something. I observe an input, I observe an output, right, and D is this full data set. And we, that data set may or may not have been generated from a standard linear regression type equation. Could have been. These things together. So if that's the, so now we can write Bayes' rule, which is what is the probability of a given weight set given the observations? Because that's basically what you want to know, right? We have this set of observations, we've got them, and now I say, okay, given those observations, what are, which sets of weights are more or less likely? Because where we're going to go with this, of course, is we're going to take the high likelihood ones in some sense. So which sets of, so now we can use Bayes' rule, and we can say, okay, what's the probability of D given W? Probability of W, probability of D, right? So now we can write this as Bayes' rule. Well, you say, well, what do I know about that? Where did this thing come from? What's probability of D given W, right? Why would I know that? Well, if I knew what W was, I could say how likely would it be to get this particular observation, right? Because it's, if it turns out that y1 equals wx1 for a particular w and yn equals wxn for a particular w, and it's all the same, that's the w, right? For that particular w, I can say, okay, I've got a very good fit. Like, how likely was this to have occurred? Right? And I could also say if w was the wrong w, I wouldn't have a very good fit, right? So it would be pretty unlikely to get that. And again, I can generate that from this equation, because if I know the probability density of E, so if I know something about the error term or the noise term there, then I can calculate exactly what would be the probability of observing a particular y and x for any value of w. It's just a calculation I can do. And so now I want to go the other way around. I want to say, okay, but I know that. That's called the likelihood function. I know the likelihood function. And what can I convert? Given a particular D, now can I find the best W from it? Right. So this is sort of saying, given a particular W, how likely is D? And the okay. So the important thing here is that this P of D given W can be considered an observation model. W is a hidden variable. Right? You don't see the weights. We have a model of the world. We think this model of the world involves these weights, but we never see them. What we see is this observation, which is the set of inputs and outputs. And so we say, okay, this is the observation model based on our assumed model of the relationship between the weights and the rest of the world. We think there are these weights in the world. We think that W is something out in the world. We can't see it, but we make a model of it. What is the observation model based on that? What would it look like, right? If there were in fact, 3 cats and 1 dog out there, what would I be seeing now, right? And now you want to go the other way. Given what I'm seeing now, what's the chance that there's exactly 3 cats and 1 dog in the image? Right. So the point is that usually this likelihood function, that observation model, is something that you know about, is something that you can create. It isn't always, but this is the situation where Bayes' rule comes up with it. You can think of y equals W transpose X plus epsilon as an observation model, right? This tells you, how do I go from W to some probability density over D, which is the pairs of Y and X, right? So this does give me that information, right? The observation, your model, your statistical model is basically an observation model. And then there's a couple of things. So this is saying, what's the probability of each set of weights W, all possible weights. And in general, here I was writing it as W, but you could do this over models, right? So you could say, I've got a couple of models of the world. One model of the world might be Newtonian mechanics. One might be quantum mechanics. These are 2 different models of the way the world works. Each model, different models make different predictions for observations. I make an observation and I say which model is more likely of those 2, right? And so if you're looking at the differences between classical mechanics and quantum mechanics, they will match for large objects at slow speeds. And so you won't be able to distinguish very much what is going to happen at those levels. So either model might be equally likely. But if your observation happened to be a very small object or something operating at very high speed, then all of a sudden you're going to have non-classical mechanics. You'll be able to distinguish the models. Right? So different observations are going to lead to different relative probabilities of the models. You can select between multiple possible models in the same way. So again, often we have this, but in the sense that we know what this is. If you think of this is science, right? Science makes a prediction. This is what I think is happening. This is the hypothesis about what would happen if that were true. Then we say, okay, what did happen? Which of the various hypotheses is more likely to be true? Okay. Now, so what about this term here? What is that? That term is how much which model did you believe in advance? Okay. So I have let's say I see a dog in front of me, and I have 2 possible models for that dog. One of which is that the dog is a vicious creature that is going to attack me, and the other is a nice, sweet, wonderful dog. And each of those models makes a prediction, right? The vicious creature predicts that the dog is going to bite me. The sweet, wonderful dog predicts the dog is not going to bite me. So I just wait a while and I see if it bites me, right? And based on that, I can make a prediction about which dog I'm looking at, right? Maybe the species of the dog, maybe something about its owner. But I also had some information as that most dogs don't bite. So I wasn't really expecting to get bitten, right? So that's my prior assumption about this. And what does that that do, it sort of biases your choice of models. So it says, look, even if the dog bit me, most dogs really are very passive. And so it bit me, but maybe that doesn't mean it's a vicious animal. Maybe something scared it, right? I have, you make an assumption. That's your prior assumptions about what the world is going to be, right? I hear I hear a sound outside, and it sounds like a car driving by, but it could have been it could have been somebody who was making car noises with their mouth. I think it's more likely that it's a car. So when I hear that sound, but either one could be, I have equal chance, right? I hear the same sound. I don't know what it came from, but I live on a busy street, so it probably came from a car. Right? So the idea is this essentially biases your observations. Now, you don't have to bias it, right? You could say, look, I have no basis for choosing here, right? I think there's a lot of cars that drive by, and I can't tell you if that, I cannot tell you. I think there's an equal probability of a Nissan and a Toyota driving by. I hear a sound, a car comes through, that doesn't allow me to distinguish between them. So I can't tell, right? Or I could say, well, the Nissan factory happens to be down the street from me. I hear a car driving by. They all sound the same, but I live near the Nissan factory. Probably it was a Nissan. Right? So that's independent of the observation, right? The observation didn't help me make the model, choose a model. It's my prior helped me choose the model. Those are called the priors. Why does nobody ever care about this denominator term? Everyone always ignores the denominator term, and that's the probability of the observation itself. And the idea is because that doesn't help you choose the model. You're always doing something. You're always saying, which M is it? And P of D does not depend on M. So no matter what you're doing, this part doesn't depend on M, so you really don't care. It's basically a normalization term and makes everything add up to 1. So you'll see people ignoring it a lot. For instance, if you're trying to say which is the most likely model, you'll do this, right? Which is the most likely model. So if I have an observation D, and I say, okay, which of a bunch of different models is the most likely one? I'm going to say, pick the model that has the highest probability given the observation, right? And that's called the maximum a posteriori estimate, because this term includes both my measurement model and my prior, right? So this is that gives me the highest. But I could, when I'm doing that maximum operation, right, of PM comma D, again, it's PD. Sorry, I have to get my handwriting. That's P of D M times P M divided by P of D, right? And I'm maximizing over M. So it's just as good if I delete that bottom, right? I'll still get a maximum, right? It's still going to work. So that's why the bottom thing doesn't matter. If you're just maximizing, you don't care. The only reason that you need the denominator is to make the thing turn into a probability and satisfy the rules of probability. That's different when we look at thermodynamics models later. There's a very different meaning of what that denominator is. It becomes the distribution function. Well, that does have some meaning, but in this context, it doesn't. Now, there are other ways to do this. So here I'm looking at when I have a probability density, I could say, let me suppose I've got a skewed probability density. I could say what value of X gives me the peak of that probability density. And that's what we call the MAP estimate. It's called, let's say that this is the, let's say that this is the conditional density of X given Y. Right? So for some particular Y. So the MAP estimate is the peak there, right? But I don't have to do the peak. I could look at the mean, and the mean of X might be here. It might be a little bit off to one side if the probability density is skewed, right? So that turns out to, these minimize different things. The maximum a posteriori estimate minimizes the probability of being wrong, right? Whereas the minimum mean squared error estimate minimizes the mean squared error. So one of the examples I like to give is if you observe, you take a large number of people and you take a large number of people, say, and some of them have I'm trying to think. Well, so let's take like dogs and cats. You observe animals. You've got some dogs, you've got some cats, right? And I observe this many dogs and I observe this many cats, right? So the maximum likelihood estimate. So now I'm going to say, okay, I pull an animal out of the bag at random. I don't look at it as more likely to be what's it most likely to be? The maximum a posteriori estimate is that it's a cat, just based on what I've seen before. Like most of the time I get cats out of this bag, right? Sometimes I get a dog, most of the time I get a cat, right? But the minimum mean squared error estimate is going to be in here somewhere, right? It's going to be neither dog nor cat. So it's worth realizing that minimizing the mean squared error, if I assign a -1 to a dog and a +1 to a cat, the MMSE error, the MMSE estimate could be like a 0.8. You say, well, what the heck is a 0.8? Well, we don't know, but it minimizes the mean squared error, right? So it's just, but that's just a way to remember the difference between these things, and it's a little bit like saying what's the the most, well, it's most likely versus minimum error, and there's different types of error that you can use, and sometimes error matters in different ways, right? If your goal in life is to separate dogs from cats, you want to be 100% correct in what species you're looking at. But if your goal in life is to say, what is the probability that a cat would come out of this bag, then that's a number that is neither dog nor cat. It's a probability value, right? So that you can get different, it depends on what you're trying to get. Now, suppose that you don't know, you don't have any prior estimate of what PM is, right? So you don't have a prior guess as to what your model might be, or in this case, you don't know, you don't have a prior guess as to what the weights might be. So you say they're all equally likely, right? That's the equal probability assumption. Like I know nothing to begin with, anything's possible. Well, then that's a constant. And then in that case, the probability of D given M is equal to the probability of M given D, right? So that makes life easy because P of M is a constant. Okay. So what would happen if P of M is not a constant, but I use P of D given M anyway? So I maximize over M of P of D given M, right? So what I'm doing there is I now calculate what's called the maximum likelihood estimate. And the maximum likelihood estimate is not the same as the maximum a posteriori, right? Maximum a posteriori says, given the observation and given my prior assumptions, what's the most likely answer? Maximum likelihood estimate says, what answer is most likely to have generated the observation that I saw? Okay. Now, P of D. So what you're tending to do now is when you're calculating when you calculate a maximum likelihood estimate, you are maximizing over M of the probability of D given M. Right. So it's the same as the MAP estimate if you knew nothing to begin with, if you had no prior information. But it's different if you do have prior information, or you can think of it as ignoring prior information. Right? It's what happens if we want to we want to look just at the observation. In my world, for instance, when I send a child for an X-ray or say they're getting an MRI of their brain, the radiologist will look at the MRI scan and they will tell me exactly what they see. They don't want to know what I thought was happening. Right? I may say, this is a child who I think, based on my examination, I think they've got a brain tumor on the left side of their brain. Right? And what the radiologist wants to do is they want to say, well, I don't want to be biased by that. I just want to look at what I see without knowing what your prior guess was. And then it's my job as the clinician to take the the likelihood function from the radiologist, which says, this is what I see, to combine it with my prior, this is what I think is happening, and to come up with what I consider to be the posterior estimate, right? So the point is that there are situations in which you actively attempt to ignore the prior data so as not to bias your thinking. Humans are strongly biased by prior data, as we should be. If you never paid any attention to prior data, you'd never learn anything. So the prior data is critical to us, but it injects your prior data is the result of your entire past experience of your life, might be different from someone else's prior data, so that if you're trying to get consistency out of human behavior, it's a good idea to try to train people to ignore priors as much as possible and just consistently look at the data that's in front of them. And if you do that, you're generating the maximum likelihood estimate. So the question then is, of all the models that could be going on here, which one predicts the data the best, or which one is most likely to have created the data? Now, interestingly, remember that the integral of a probability density of d dd is equal to 1. That is always going to be true. However, the integral of this pd of m, so dd equals 1, but that dm does not have to equal to 1. This is not a probability density over m. So the likelihood function does not necessarily add up to 1. It can, but doesn't have to. It's just a function. It's a function of m. And that function of m can be maximized like anything else. So now, again, we'll get into this a little bit more. There is this sense in some way that the likelihood function, P of d given m, and the Bayes posterior distribution, P of m given d, in some sense, look a little bit like inverses of each other. And so people often talk about this as belonging to a class of inverse problems. We're trying to invert something, a function. And again, we'll come to that much more when we look at Monte Carlo methods. Okay. So I included here some things I'm calling fun facts about the conditional expectation operator. Now, where do we get, why is the conditional expectation operator important? Or what, for that matter, what is the conditional expectation operator? Let me back up for a second. So conditional expectation, remember the expected value over some probability distribution of x is equal to the integral of x, p of x, dx. The conditional expectation, which is often written as the expectation of x given y, like that, really means the expectation over the conditional density of p of x given y of x. And that's equal to the integral of x, p of x given y dx. And is therefore a function of y, right? Because this is, y just becomes a parameter. Okay? And why is that important? Remember, that's this. So this is the minimum mean squared error estimate. So the conditional expectation operator is the minimum mean squared error estimate of one thing from another. So the conditional expectation operator it's an estimator, and it's a function, right? It basically takes, e of x given y. It's a function of y. But here's an interesting thing. So now look at the conditional expectation of some function g of x of, in this case, z. Could have been y anyway. So take some function g of x given z. What does this mean? So I'm just going to write it out just the way you'd normally write it out. Writes out like this, and I could say it's a function of z. But look at this. That could just as easily have been g of x e to the negative I omega x dx, right? Or I z x dx, right? That's a Fourier transform, right? Or it could just as easily have been the integral of g of x, x to the z dx, right? It's a Taylor series, Taylor expansion, right? So the point is, one of the ways you want to think about this conditional expectation operator is it's a mapping from this function g of x to a function f of z, right? Think of how Fourier transforms do that, right? They take g of x and they map into, g of omega, right? Where omega is a frequency. These things are convertible between each other. You can convert back and forth, and that this these may or may not be convertible back and forth. These P of X and Z may or may not create a complete set of functions that allows inversion. But P of X and Z is essentially a basis set which allows you to map between different domains. Now, again, I'm moving very quickly back and forth between different levels of this. But the point is to think about the conditional expectation operator maps between two domains. But what is it trying to do? Again, it is back here. It's trying to get you an answer. It's trying to get you a minimum mean squared error estimate of one thing from another thing. So all estimation is trying to take one thing that you see and estimate something you didn't see, right? And the thing you see might have some function like g of x, which could be a likelihood function over x. And the thing you didn't see might be, some other function of z, which might have its own likelihood function or probability density. And you're symmetrically, you can observe one and estimate the other. And all of these functions are designed to do that. The conditional expectation operator does that, and it moves from one domain to the other. And these, so it transforms between these. In this case, this is a linear transformation. So it's a linear operator. This thing is a linear operator. And it's a linear operator that moves between domains, right? The general linear operator in a Hilbert space would look like, it'll look like g of x, some operator k of x and z dx, right? And then this will give you some g of z equals that, right? So that's a general, and the point is this k of x and z is the conditional density, and the way I've written it here, p of x given z will move these things back and forth. And P of Z of X will move it the other way, right? And I call these fun facts because this may or may not come up. Haken doesn't talk about this in this chapter, but again, when you're thinking about these probability concepts, we'll come back to this in another number of other domains. But remember, the conditional expectation operator is the general form of a minimum mean squared error estimate of one thing from another. And it's very closely related to these concepts in Bayes' rule. It's worth knowing, thinking about what happens if one of these is continuous and one is discrete. So in this case, if x is continuous and z is discrete, remember E of z and x looks like a function of z, right? Because it's the average over all the x's. The x is going to go away. It looks like a function of z. So if x is continuous and z is discrete, the expected value of x given z is discrete. So suppose, and this is an example, x is temperature, and z is a measurement taken on an 8-bit thermometer, right? So z is discrete. I've got 256 possible values. So the expected value of the temperature, right? So I'm going to measure temperature over a bunch of different days on these thermometers, right? On this, well, I'm sorry. Let me put it differently. What's the expected value of the actual temperature, given that I observe a temperature of 100 on my thermometer, right? The expected value of that is going to have some values. Hopefully, it's around 100. If I observe 101 on the thermometer, I get a different expected value for what the true temperature is. Maybe it's around 101. But I've only got 256 things I could see on the thermometer. So I've only got 256 possible measurements. So I only have 256 possible expected values. If you go the other way around, x is discrete and z is continuous. Now what happens? Expected value of x is z is continuous. So now I'm gonna say, suppose I have and again, remember there's no true thing as a continuous measurement, but we'll say it's sort of more precise. So in some sense, z is more precise than x. So now I just want to say x is discrete, and maybe I just want to know, is it? We can use the same thing. Is it hot or cold today, right? And I'm just going to say arbitrarily that all hot things are higher than 100 and all cold things are less than 100. So I just want it. So that's discrete. Is it hot or cold today? And I take a temperature measurement. And maybe I take a bunch of temperature measurements, right? And I get some values, what's the expected value over x of z. So what's the expected value over whether it's hot or cold given a particular temperature measurement, right? And this, again, there's going to be error on this. So suppose that my temperature measurement says exactly 100, right? The question is it hot or cold? Well, I'm right on the boundary, right? And so what's going to happen is that I'm going to get a 50% probability, right? I'm going to get sort of a hot-cold mix because it's the average of hot and cold is like warm somewhere, right? So if the measurement of z is 100, if the measurement of z is 100 plus 10 to the negative sixth, it's going to be a little hotter, but it's still going to be a hot-cold mix because the noise is going to spread these things out. So the point is that you will have e of x of z is continuous. Again, it's a function of z. Go away. It's a function of z. So it'll be it will have a continuous distribution. Anyway, it's just worth keeping this stuff in mind, and this will happen a lot, particularly when you start applying networks to discrete versus continuous data, and you're going to wonder why you're getting funny answers. Good. Now, there are a couple of other things going on here. So Haykin spends a lot of time looking at the relationship between Bayes' rule and linear least squares estimation, and he goes through the full derivative of this. I'm going to do this in a much simpler way, but try to show you a little bit of the relationship between these things. Again, suppose we have our typical model, our typical linear model. This is what we think the world is. And now from last class, we saw that the optimal estimate of W hat is RXX inverse RYX, right? Where RXX inverse is RXX is equal to the expected value of XX transpose, and RYX is equal to the expected value of YX. So this is this is a vector if Y is scalar, and this is a matrix. And then when you try to make an estimate of Y from a particular value of X, it ends up looking like this. Or typically people might write it the other way. They would write it as Y hat equals RYX, RXX inverse times X. Okay, and so this is the minimum mean squared error estimate of Y from X, right? Or which we could write as the expected value of Y given X. And you can, and Haykin basically does the proof of this, but this is how you solve that. And because that's the expected value of Y from X, we could call this thing here W transfer. And if we set W transpose, if we set W transpose equal to RYX, RXX inverse, then Y hat equals W transpose X is the minimum mean squared error estimate of Y hat from X, right? So now we've approximated the data set that we wanted, the YI data set. Right? So we've approximated that. Okay, but let's look at what these terms actually look like. So RYX, RXX, and what does RXX inverse actually do? So again, RXX is equal to the expected value of XX transpose, right? So what happens if RXX is the identity? That means that the elements of X are all unit norm and uncorrelated with each other, right? That's a perfectly possible thing. In which case, you could just get rid of it. Y hat equals RYX X for that case, right? And that's that. So that. And that's fine, right? And that will be the true case. So what happens? What is the RXX inverse actually doing? Well, it's saying, well, X doesn't look like that, right? So suppose X were two-dimensional. If X were two-dimensional, if the probability density is sort of long. I'm sorry, it doesn't lie along the line. If X were two-dimensional and Gaussian. So this is X1 and X2, two components of X. It will be circular like that. And that's the case where RXX equals the identity, right? Where there's no correlation between the two, right? But suppose it's not circular. Now we have an RXX, which is not equal to the identity. What does RXX inverse do? It will spread this stuff out. It will make it look, it will modify the X Only if my pen continues to work. It will modify, it will spread out the axes in such a way that this sort of non-circular thing will become circular, right? So Rx, X inverse X, the autocorrelation function of that thing, let's suppose we call that U. So now RUU is equal to the identity. So it just kind of, it whitens it, right? It's a whitening filter, right? So, but think about what this means in a Bayesian context. That's kind of what you knew ahead of time about your input, right? So what's happening here is that one of the relationships between the Bayesian and the sort of more standard linear formulation is that this term in the linear formulation basically encapsulates your second order prior knowledge. It's not everything about X, but suppose you knew that X was Gaussian, then the only thing you care about is, and suppose you knew it was zero mean, then the only thing you care about is its variance terms. And so this autocorrelation function is everything you know about X ahead of time. Now you can calculate by measuring X, but the point is that that was what you knew about X ahead of time. And so this process of whitening the input has a similarity to the concept of prior knowledge. And so one way to think about prior knowledge is, what do I have to do to remove prior knowledge? And that's again, this is we'll see this more when we look at the role of hidden units. But and there's a lot of different ways to think about this. But I just wanted to point this out because it's important when we look at these terms, at this sort of the standard equation for linear estimation, to recognize that it satisfies Bayes' rule. Remember, Bayes' rule is true. So anything that does estimation is going to have little pieces of Bayes' rule inside it. Okay. The bias variance trade-off. Where does that come from? And what does this mean? This gets very confusing to people. The simplest way to think about it is from these pictures that I took off the internet. I don't know, there's a page written by Seema Singh. I'm not sure if this figure comes from him. I don't know who Seema Singh is. It was just the page was attributed to him. When you have a series of points here, so in these cases, you're looking at, you've got some blue points, and you are trying to fit a line to it. I could fit this way, or I could fit this way, or fit that way, right? And these lines mean different. What do these lines mean? The lines, the red lines are the set of possible models. So the red line is the model, right? Now, how many models do I have? Right. So in this case, I have lots of models, right? Because I have to be able to fit a different red line to every little arrangement of points that I might possibly have. But I'm going to fit very well, right? I have lots of possible models. In this case, I only have one model. It's a straight line. I'm going to fit the same thing to everybody, right? One size fits all. So here are a small number of models. And here, maybe I have a few models, right? I have models, they all have to be smooth. So maybe these models are I don't know, second, fourth order polynomials or something, right? So I have just a small number of models. And so so what happens? I also have, so I have the number of models, and I also have the number of data sets, right? And the number of data sets is the number of little blue dots that I might have, right? So I could pick a different set of blue dots that might look similar, but might not be exactly the same. So if I pick a particular, so the bias is how well does the model fit? Okay. So in this case, my model fits very, very well. I have very low bias, right? And I choose that model. But now what happens if I choose a different data set, right? So now I observe something else. So here maybe I'm fitting, maybe these are the heights of people as a function of where they live, right? So I fit this data set very well, but I now choose a different group of people and I measure their heights and I say, where do they live? So I'm going to get different little points, right, in different places. And I fit so the model is going to fit very well to one particular data set, and in general will fit very badly to other data sets. So I will have very high variance over the set of data sets, right? If I choose a different set of data, I'm going to get completely different variance, right? In this case, I'm going to have very high bias, so my model doesn't fit very well, right? But the model itself isn't going to change very much. Let me back up a second. Here it's probably better in this model to think of the variance as being over the weights. Let's suppose I've got some set of weight parameters that describe this model. The weights, so the model is a function of some weights. So here, if I choose a different data set, I need to choose a different set of weights, right? So there's going to be very high variance in the weights as I choose a different data set. In this case, I really don't have any weights at all, right? I've just got one model. So if I choose a different data set, I get exactly the same weights, right? So in this case, if delta of your data set goes to a big change in the model, right? So I get lots of changes in the model. In this case, a change in my data set goes to 0 change in model. So this is a big change in model, that's a 0 change in model. And in this case, if I change my data set, I get a little bit of change in the model. So I get a little bit of a change in the model, right? So you talk about the variance of the model or the variance of the weights within the model as a function of your data sets. Now, in this case, my fit isn't so good, and in this case, my fit is a lot better, right? So the more models I have, the better my fit to any particular data set. But the more variation, the more I have to change my model as I get different data sets. The reason this is important is what happens if you're trying to extrapolate, right? So if I have a data set that looks like this, right? And I just observe this section of data and I fit a model to it. If I fit a straight line model to it, maybe I can extrapolate and maybe it's going to fit okay, right? But what happens if I fit a model that does this, right? Now where do I go, right? So the point is that if you have too many possible models, you don't constrain. You may have very good, very low bias on your training set. But because you have so much variance in the choice of models, there's many models that would have fit that. That one would have fit, this one would have fit, that one would have fit, all of these things would have fit because you have so much variance in your data set. And so your prediction becomes much worse. So there's a trade-off. So these models are very complicated, and these high variance models are very complicated and have very good fits, but tend to have very poor generalization. So the point now is, how do you trade these things off against each other? Because of course a model like this has very low variance. You always get the same model, but just isn't a very good fit, right? So for instance, if my data set looked like this, and all I could do was fit linear things, I'm also going to be bad, right? So I need models that have something to do with the data set. Now, whether a model is good or not depends a lot on assumptions. So what do you care about, smoothness of a model? So consider the situation where I'm trying to predict the weather over the next couple days, or consider the situation where I'm trying to predict the next ice age. So I want to predict the weather over the next 1,000 years, right? Those are both models that could have high bias or high variance, right? But the model over, so here's my weather for the next couple days, and my weather for the next couple, and so for that model, I might want something that actually fits nicely like this, right? But if I'm trying to predict 1,000 years, I don't want that model. I want something that's going to say, look, I don't care about those things. I want something that's much smoother. So what it is that makes a good model depends on what you're trying to do with it. And again, we'll keep coming back to that as well. But the idea is that the right answer depends on what you intend to use these things for. So this bias variance trade-off is with respect to the ultimate purpose. Sometimes you just want to fit data, right? I just need to fit the data. I don't care. And I'm going to, I just, basically it's a way of memorizing data. And it's just literally a transformation of the data from one place to another, right? So for instance, a Fourier transform has with the same number of points as the input. It's just a transformation, right? It has extremely high variance. New input signal is going to give me a completely different output signal, right? So very high variance, and it makes no predictions. So a Fourier transform makes no predictions. It's a very low bias, very high variance. But now suppose I do a Fourier transform and I low pass filter it. Now I'm not going to fit that well, right? So I will have higher bias because I won't fit the high frequency components. But I might have lower variance if the signals I care about happen to be low pass signals, right? So now I'm going to have better generalization from that, right? So that when you low pass filter a signal, you're making an assumption about what parts of that signal are important. And so again, that's the bias and variance is related to where the information content is located. But this is the concept of the bias variance trade-off. You can prove it in a variety of different ways. The simplest way to do it is just noticing that if you just express error as the mean squared error between truth and your estimate of truth, you can separate this error into two terms, one of which looks like a bias term and one of which looks like a variance term. So this term is how far am I off the model I've chosen, and this term here is how much does that change based on the different data sets. So you have the bias and variance terms are related to again, how much flexibility do I have in the model? How much flexibility is in the data set? When the book talks about the minimum description length, the approach to things, MDL is all of these things look like model complexity plus error complexity. So the model complexity, again, the more complex the model, the better you'll fit. But the less complex the model, the more error you'll get. When I say error complexity, it's sort of the amount of information in the error. The question is, how do you describe model complexity? It can be the number of variables, the number of weights. How do you describe error complexity? It can be the total mean squared error. It could be lots of different measurements on that. They point out that one of Kolmogorov's original descriptions of model complexity was the length of the shortest computer program that could generate the data. Now, whether what does a length of a computer program mean? But you can quantify that in some way. But again, this is an attempt to say how can we quantify these things in some way? So the minimum description length. So when you describe something, you say, okay, this is my model, and this is how hard it takes me to describe it, and these are the errors it makes. This shows up a lot for those of you who've done work in radio or any other kind of transmission lines or any kind of communication. You will often have, let's take some kind of a predictive observer. Let's suppose that I am trying to transmit some value X from a transmitter to a receiver Y. Or actually, let me make it so that what I'm trying to do is the receiver is trying to estimate X based on the received data, right? So there's some observation that comes in there. Right. And one of the ways that you might do that is you might know something about X, right? I might know that X is smooth. So what I'm going to do is I'm going to predict here, and instead of transmitting Z, I'm just going to transmit, and here I'm going to make a little estimate X hat, and I'm going to transmit X minus X hat, right? I'm just going to transmit my error. This thing takes X hat, makes its prediction X hat, adds epsilon back in, and reconstructs X hat from here. So now it gets the same thing there, right? So people are hopefully used to this kind of way of thinking, right? So in other words, if the transmitter makes its best prediction, the receiver makes its best prediction, the transmitter knows the error, sends just the error, the receiver just incorporates that error back in, and now the receiver makes a prediction that's now going to be identical to what occurred at the transmitter, right? This is the standard Whitening filter. And those predictions can be nonlinear, right? You can do something very complicated. That prediction could be a word predictor based on English. It could be something about smoothness. It could know something about the thing that's being sent, but it's a very good way of reducing information. So what's going on here? The more complex, the better the transmitter can predict the next symbol to be sent, the less error it has to transmit, right? So there's a trade-off in transmission between the quality of your predictor and the amount of data that needs to be sent over your transmission line, right? And so it's exactly the same thing, right? There's this trade-off. Now, if the predictions may not be possible because there could be noise or unpredictable components, or it may not be possible because you don't have the computational power to do it, but there's nevertheless going to be, you make your best prediction. Now, suppose that prediction is awful, right? If it's not very good, you're going to end up transmitting more and more errors to the receiver. So you want your prediction to be good. But again, your prediction could be awful. It itself will have its own bias and variance, which will feed into this. And so you want your predictor on the transmitter and the receiver to be appropriately tailored to the information you actually want to send. Because now, in fact, the receiver does not have to be a perfect replica of the transmitter. It just has to reconstruct the components of the music that you're interested in listening to. But it's worth being aware that this is all the same idea, that you have a computational predictor and an error term, and that these things show up in a lot of different fields within electrical engineering. I put some notes in here just in the last minute or so. I'm running a little bit over here. This came up in the homework a little bit. I had a couple questions from people on the same issue, which is basically this question here: how do you regress y on x when y is binary? There's lots of good things. This is the concept of logistic regression. There's lots of good explanations of this stuff online. The basic idea is, and the reason that this is important is this becomes very important when we look at neural networks based on spikes. So you might, so neurons fire spikes. They either fire or not, so it's binary. How do neurons represent numbers? It's in the spike rate or in the probability of spiking. So information can be transmitted in terms of probability. So instead of regressing y on x when y is binary, here, what you do is you regress the probability of that y equals 1 on x. And that probability is non-binary, right? Even though the output is binary, that probability is not a binary number. But you still have a problem because probabilities only live between 0 and 1. So we want to, and whereas wx does not live between 0 and 1. So what we do is we use this logit function, which spreads 0 and 1 into negative infinity to infinity, right? So we spread that out so that now if you regress logit of the probability on x, now we've spread, this thing has the range of negative infinity to infinity, as does that. And so now you can do a regression. But we don't know those probabilities, right? I mean, you don't see these probabilities. Nobody handed it to you. All you have is samples of zeros and ones. So what we do instead is we can do the other way. We just take the inverse of the logit function, which and when you invert it, you get this. You get probability looks like that. And now you regress p on the inverse logit of wx, right? But we've seen this before, right? That's the sigmoid function that we were using for neural nets, right? That's a sigmoid neural net activation function. So it looks just like, we're right back to the perceptron or the McCulloch-Pitts model. So the point is, and again, I want to make that analogy, which is that these nonlinear functions have this interesting property. Logit isn't the only function you could use, but these are nonlinear link functions used in the concept of, this is within the context of generalized linear models in statistics. And what happens now is you regress the probability on this function, which has mapped the input into the range 0 and 1. Now we still don't have the probabilities, right? All we have is y, which is either 0 or 1, but not both. But it turns out, and I put the proof in here, down here, it turns out that it doesn't matter. So if you could do the regression of p on the sigmoid function of w transpose x, or the regression of y on the on where y is binary, right? You'll get the same answer, right? If you minimize the mean squared error, you'll get the same answer for w. This regression, trying to do this, is a nonlinear regression. You can't solve that using linear methods. That you require a nonlinear method, including neural network methods to do this. Backpropagation will solve this. There's a variety of methods. But the point is that becomes, this is the classic neural network perceptron McCulloch-Pitts model attempts to solve the logistic regression problem. And this isn't where it came from, but lots of good ideas converge to the same place. And again, you can, in many of those situations, you do have a continuous output y, but even if y is binary, if you do this regression, you will get the correct logistic regression for that binary case. So I will leave it there, and I'm going to keep the Zoom open for a bit. And if people have questions, you're welcome to stay on and ask me questions. I will, I guess our next class is on Monday, and I will, and I'll look at your homeworks over the weekend, hope to get you all that back before then. Yeah, thanks very much. So I'll be here.